Superior Essex manufactures its fiber optic cable products in a state-of-the-art facility located in Brownwood, Texas. Here, we produce hundreds of different fiber cable designs, including loose tube, ribbon fiber, and tight buffer constructions for outside plant, fiber to the home, indoor, outdoor, and premises applications. In this video, we will guide you through the principal manufacturing processes for each of these three basic fiber cable designs. The first step in fiber cable manufacturing is the inspection and testing of optical fibers. While Superior Essex does not manufacture its own optical fibers, each manufacturer that supplies our optical fiber glass must meet exacting requirements for performance and reliability. This approach allows us to offer our customers a choice in the brand of optical fibers selected for the finished cable and gives Superior Essex supply flexibility in the event of optical fiber shortages. The optical fiber received by Superior Essex can vary in length from 4,400 to 50,000 meters and is categorized based on fiber performance characteristics. As part of our manufacturing process, every optical fiber within every fiber cable product can be traced throughout each step of production. The clear glass fibers initially undergo one of two types of coloring processes: UV inking, which colors it in preparation for ribbonizing, and loose tube processes, or tight buffering, which provides both color and a protective coating. In the UV inking process, a specialized ink is coated onto each optical fiber. One of 12 colors is used to properly identify the optical fiber within the tube or ribbon in accordance with industry standards. After the inking step, the optical fiber quickly passes to a curing enclosure that rapidly cures the ink to form a permanent color coating and then wound onto a take-up reel. The color-coated fiber is now ready to be put into loose tube or made into ribbon fiber. For tight buffer cable products, a colored PVC coating is applied that increases the diameter of the fiber from 250 microns to 900 microns. This process is called tight buffering, which, in addition to providing a color to identify each fiber, allows the resulting cable to be flexible, yet rugged and easily mated to mechanical connectors. For these reasons, the tight buffered cable design is the preferred fiber cable design for indoor cable applications. At this point, fibers destined for loose tube or tight buffered cable proceed to the sheathing or tubing process. Fibers destined for ribbon fiber cables must undergo an additional intermediate step called ribbonizing. Fiber ribbons are created by serving 12, 24, or 36 individual fibers side by side into a coating die that encapsulates the fibers with a UV curable matrix material into a fiber array. In a process similar to the inking process, the ribbon leaves the coating die and passes through an intense ultraviolet light source that cures the matrix and solidifies the ribbon. The completed fiber ribbon is then wound onto a supply reel. Before the ribbon can be used in any cable, however, it must be tested to verify that its structure and dimensions meet specifications. A small length of ribbon is cut from the reel and placed under a microscope. A technician carefully examines the ribbon sample and fully documents the results. Only if the sample passes inspection can the reel go on to be used in a fiber optic cable. All three of the basic fiber cable designs, loose tube, ribbon fiber, and tight buffered cables, require some form of sheathing process. This is usually another intermediate step, but can be the final production step for small premises cable designs. Here we see a sheathing process for OSP fiber cable that begins with a number of reels of color-coded fiber loaded onto a machine that supplies each fiber at a constant rate under computer-controlled tension. The fibers come together and are fed into an extruder head that performs two main functions. First, a flow of moisture-blocking gel surrounds the fibers. Then, molten colored plastic is extruded around the fiber bundle to form a loose tube around the fibers. Immediately upon leaving the extruder, the hot, soft tube is passed through a long water-filled trough that slowly cools and hardens the tube. The completed tube is passed through an optical micrometer to verify its diameter is within specifications. It is then wound on a take-up reel to be used later in the cabling process. As part of our quality control process, we periodically test fiber tubes to verify that there is sufficient slack fiber within the tubes. This additional fiber slack, also called excess fiber length or EFL, allows the cable to expand and contract around the fibers without causing stress or attenuation problems. To perform this test, a section of a tube is placed on a special test fixture that accurately cuts it to a predetermined length. The tube is opened midway along its length and the fibers are removed. One of the fibers is separated from the bundle and is mounted between a pair of measurement blocks. A micrometer wheel is carefully adjusted to just bring the fiber into tension. A digital readout displays the fiber length, which is then compared to the known length of the tube. In a different sheathing process, we see tight buffered fibers being fed into an extruder head along with special strength yarns. A fire-retardant plastic material is extruded to form the protective tube around the fibers. In this case, the tube is also the outside protective jacket for the now completed cable. Ribbon fibers are handled in a similar manner during the sheathing process. 1 to 30 ribbons are oscillated in one direction prior to being fed into an extruder head, which forms the tube. This oscillation allows for a predetermined amount of fiber slack to be maintained within the tube. PFM gel or dry water blocking agents are also inserted prior to the tube being formed around the ribbons. Depending on the number of fibers required, multiple tubes of fibers may be needed to create the desired cable. The process of combining multiple tubes is called stranding. Reels of fiber-filled tubes are loaded on the payoff equipment of the cabling line. In this example, we see the production of a loose tube stranded cable. The process begins with a reel of fiberglass rod that will become the cable's central strength member. Along with the fiberglass rod, a number of reels of colored loose tubes containing fibers are fed through a series of rollers and guides that straighten the tubes and position them in the correct relationship for the next step in the process. The strength member and tubes then pass into a machine that winds the tubes in a reverse oscillating wrap around the central strength member. Here, you can easily see how the wrap periodically reverses. The cable is then covered with a layer of moisture-absorbing tape. This unjacketed cable subassembly can be used later as the inner layer of a multi-layer stranded cable, or be surrounded with steel armor for use in an underground cable, or simply be covered with an outer jacket for general-purpose applications. The final phase of fiber cable production is the jacketing process. The materials used for the outer cable jacket are chosen for the intended application of the fiber cable. For most OSP fiber cables, Superior Essex utilizes medium-density polyethylene due to its durability, moisture resistance, and low coefficient of friction. High or low-density polyethylene can also be used for select OSP cable designs that require different performance characteristics. Polyvinyl chloride, or PVC, is typically used for the jacket material in our premises cable designs. PVC is a thermoplastic with good flame and abrasion resistance, making it suitable for raceways, indoor-outdoor cable structures, ducted environments, and most riser-rated and plenum-rated locations. The jacketing line begins with the reel of partially completed cable we saw manufactured earlier. This cable passes into a machine that spins a series of flexible fiberglass strength members in a web-like configuration around the cable. The web-like design avoids torque problems, which would cause the cable to have a preferential bend. In order to make it easier to access the cable core where the tubes and fibers are located, one or more high-strength ripcords are added. Here, the red ripcord is seen traveling parallel to the cable as it moves toward the jacket extruder. The jacket extruder is simply a scaled-up version of the tube extruders we saw earlier. Molten jacket material is injected at high pressure and formed around the moving cable. When the cable leaves the extruder, it is very hot and quite soft, so it must pass through a long cooling bath while being kept straight to prevent the cable from developing a permanent curl. When the cable exits the cooling bath, it is passed through an optical micrometer to verify that its diameter is within specifications. Cables used in direct buried applications often require corrugated steel armoring to prevent rodent attack as well as damage from sharp rocks. The corrugated steel armor is formed from flat steel tape that is supplied on large reels. The cable, armor, and a ripcord are fed through a forming tool that wraps the armor around the internal cable elements. The newly armored cable now passes through an extruder where the outer jacket is applied to the cable. After jacket extrusion and cooling, the cable passes to the jacket printer. Here, a hot foil printing process transfers white ink into permanently indented print, which includes cable type, fiber count, date of production, footage or meter markings, and other required information. The completed cable is then wound onto large reels for shipment to the customer. However, one critical step still remains. The cable must go through our final test process to ensure that all fibers meet optical specifications established by Superior Essex. A short length of cable is prepared to expose the fibers to be tested. In this example, the technician is testing a ribbon fiber cable. All of the ribbons within the cable are prepared and inserted in test fixtures that are sequentially plugged into an automated test station. In this way, each fiber and every ribbon of the cable is quickly tested and compared against our specifications. Once the cable passes all tests, the cable ends are sealed and the reel is ready for shipment. A copy of the test report is permanently retained by Superior Essex and is attached to the cable reel for acceptance test comparison, engineering, and maintenance records.